Hello everyone, welcome to today's ASAP seminar. Today we are happy to invite Marcos Traviso, an exceptional speaker from IST, University of Lisbon, to talking about pushing the limits of sparse attention in language models. Marcos is an assistant professor at IST, University of Lisbon. His work centers on developing efficient and interpretable NLP models. Let's welcome Marcos for his talk.
Thanks for the introduction. So yeah, as the title said, I'm going to talk more about sparse attention in LLMs. Well, we all know LLMs, right? We all know that the backbone of LLMs comes from more or less like 10 years ago, which is transformers. And if you look at like this plot of like how these new large language models are evolving, we can see like that usually all of them are kind of based on this transformer architecture. And they are fastly evolving towards having larger and larger models. But not just that, but also increasing like some capabilities, like in this case, increasing MMLU scores. Another axis of scale is in the context length. So models are not just getting bigger in terms of parameters, but also in how many tokens they can consume and generate. And this leads to all sort of capabilities. Like if you have like a model that can handle many tokens, then we can start talking about like tool usage, agents, reasoning, maybe like biological uses as well. So this idea of having a model that can handle thousands and thousands of tokens is very powerful because it allows us to have like very many different capabilities in our models. But can we just keep it going? Can we just like increase the context length arbitrarily? And well, there are some limitations in transformers. One of them is called representational collapse. In this plot, basically what we have is like, as we add ones, tokens of ones in my input, the representations become ever and ever more similar. So as we go through from one token to the another, their representation doesn't change much. So we are kind of converging into a static fixed representation. So it doesn't matter how many tokens do I add in the end, I will get the same representation. So this is terrible because I cannot have a good representation as I keep adding tokens. Another problem is called over-squashing. And in this problem, basically means that I have a lot of information from context tokens that is kind of being forced through a single bottleneck. So all these different paths from tokens connecting to each other, they usually go down to a single path, and this creates a huge bottleneck for the model. And thirdly, and perhaps more interestingly, is this phenomenon called attention dispersion, which says that as the number of tokens increase, my attention coefficients start to spread out. So I get some kind of uniform distribution in the end. So this is pretty terrible because it means that, that I'm basically doing some kind of, just a regular average of my input. So I can just throw away my softmax, everything, and just do like average of my value vectors. So these things are pretty terrible for transformers. So what's going on? Like, why is this happening? To understand that, we need to actually go back and look, okay, our transformer made, the core components is, of course, the multi-head attention module. And if you take a look inside this module, we can see that like the operation in attention is quite simple, right? You have a bunch of queries, a bunch of keys, some values. All we do is this operation here. We can have like a pi function that is applied over this big matrix, the K matrix, where this pi function maps course probabilities, and then you multiply by value vectors. So this is essentially just a weighted sum, right? Usually in transforms, what happens is that this pi function is the softmax. So the culprit of these problems, of these limitations, if you go down, is softmax. Okay, and if you look exactly like the formulation for softmax, we see that okay, there is this like exponential divided by the sum of exponentials. And since like the exponential is always a positive function, right? All probabilities are going to be positive, no matter what. Like no matter like how small they are still larger than 0, which means that all computation paths are active. So all tokens contribute, even if it's just small, slightly, they contribute something. And this means that as I go to extreme lengths, I have no focus. I start to get dispersion. Right? So maybe it would be a nice idea to better understand where softmax comes from. Right? To understand this is nice to think about this variational view, where we have like this object called the probability simplex, which basically means that is a region of space where all my vectors are non-negative and they sum to 1. Okay. So for example, in 2D, I would have like some points in space, and the points in space that are representative of probabilities, they lie in this line here. This line is basically all vectors that have, they are non-negative, all entries are non-negative. If I take the norm of this vector, it's going to sum to 1. So the probability simplex for the 2D case is actually like just a line. For the 3D case, is this triangle, right? So it's all vectors inside this triangle. They basically are non-negative and they sum to 1. And that's why I usually use this symbol like a triangle to represent the probability simplex. And of course, as we go to higher dimensions, like in the case of RD, we get a tetrahedron and etc. So everything boils down to how we can map scores to probabilities, right? If we have this notion, like the geometric notion, it becomes quite easy. Like everything we need to do is map my scores to a probability. So just map them to the probability simplex somehow. And this is like, if you go back like to 1955, this is like something very old that says that if I have a vector of scores, I want to know where is the maximum of a score. I know that it's always going to be at a position that is the corner of my probability simplex, right? So in this case, it would be like this position here, which corresponds to the argmax, right? So the argmax is the extreme example of how we can map scores to probabilities. Of course, they are not very useful probabilities, but it still is a mapping. Right? But we can do better. Like we can maybe add some regularizer to my expression, to my optimization problem, like an entropy regularizer. Turns out that if you add like a negative Shannon entropy here, recover softmax. So softmax is essentially a regularized optimization problem using negative Shannon entropy as the regularizer. It also should be called like soft argmax, right? Not softmax, but anyway. There are of course, other possible entropy regularizers. For instance, if you use the Gini entropy, you recover something called the sparse max. And if you use something that is called Sally's entropy, which is parameterized by this alpha value, we can get all this range of different mappings. Like if I have alpha that tends to 1, I recover softmax. If I have alpha equals to 2, I recover exactly sparse max. And I add like a move alpha towards infinity, I recover argmax. So all these possible mid ranges are possible values for Alpha-entmax. So this is quite nice. Like if we look at softmax, it's really easy how we can compute softmax, right? We have a vectors, I just exponentiate everything, and then I sum I divide by the sum of exponentials. That's really easy to implement. Well, for Alpha-entmax, it's also can be evaluated quite easily, right? Like in this case, you just like have a maximum between 0 and something minus some constant tau, some power here. So for instance, alpha equals to 2, which represents sparse max. I get this expression here. So it's really easy to compute. The problem here is this constant, right? So this constant is something that ensures that my output, my p vector here, sums to 1. So it's a valid probability distribution. And unfortunately, like finding this optimal constant tau boils down to solving an optimization problem, right? So like here, I received lots of questions before that people ask, okay, but why complicating so much? Like, if you really want sparsity, like just do a top k over softmax or something like that, right? So why we don't do that? Like, take a look at softmax. Here is like an illustration in 3D. Like, it's easy to evaluate. We saw that it's easy to evaluate. It's GPU friendly. It's differentiable. But the problem is that it's dense. Right? If you look at top K, it's very slow to evaluate. We need to have some sort of sorting algorithm, which means that it's not very GPU friendly. And I think more strikingly is it's non-differentiable. Like as we add tiny nodes to the inputs, suddenly we are going to move like from the indices that are the top in the ones that are not the top anymore. And this like for training, neural networks, backpropagation, that creates a huge problem. Okay, let me remove this. Whereas like for Alpha-entmax, you have something that is like the best of both worlds. Like we have something that is easy to evaluate, given that we know this constant tau. Is GPU friendly, as we are going to see later. It's totally differentiable, and it's sparse. So that's what we want. Right? So in this work called long context generalization with sparse attention, which was made it was led by Pavlo in Google. We asked ourselves, okay, what happens with Alpha-entmax attention on long sequences? Right. So we had some theoretical findings. So first, you can see the details in the paper, like for the actual proofs, etc. But some things that we found that's first, it preserves representations. So as we move like for larger and larger sequence lengths, the difference between two consecutive tokens, they are not they do not go towards zero, as in the case of for Softmax. We also alleviate over squashing, which means that like in our case with sparse attention, we are going to have some links here between tokens that are exactly zero, right? So we don't have this, we alleviate this big bottleneck that we had before with Softmax. Another thing that we found is that as long as we have sparsity, we are going to have some focus. So entmax has a propensity to not suffer from dispersion as softmax. Softmax will inevitably suffer from dispersion, but entmax may not. So this is quite cool. But what about like something more practical? Turns out that like Alpha-entmax can be too sparse sometimes. So we propose something called adaptive scalable Alpha-entmax, where we propose to have like this scaling parameter to counteract like this excessive sparsification. And this is similar to this SS max kind of work. The difference here is that like these parameters, beta, gamma, etc., they are learnable for each head in each query. In these plots, I'm basically showing like different possible fit curves for different values of delta, beta, and gamma. And something we notice is that like several heads in these transform modes, they of course they are very different from each other. So it's really important to have something that is like head dependent. And of course, this parameterization is one that works really well in practice. Another thing is that when we go for sparse attention, it's really important how we choose the position encodings in your method. So if you try to use like Alpha-entmax or maybe even top K with rope, so what's going to happen is that we are going to have some very hard cutoffs because of my sparsity that are periodic and frequency specific. So I'm going to have something that I call like dead zones. So I have here my tokens, and they, for some frequencies, they are not attended, and then for other tokens, they are attended, and they not attend anymore. So we have this kind of periodic pattern that doesn't make a lot of sense, right? In this figure, we can see a behavior like that. So here we have like for each query position, the attended centroid. So more or less where like the probability mass was focused. So with Alibi, it was basically, attending to to our sliding window, which makes sense. Uh, for rope, it was kind of all over the place. Like we can see there is a very high variance. And this is because of this periodic pattern. Uh, and we also test NOPE, and NOPE is a lot more like semantic guided. So what we propose is to use for sparse attention is something called NAPE, where half of the heads in our model use NOPE, and the other half use Alibi. So we have something like, okay, some heads focus on this short span, more like a sliding window, and other heads are more like semantic guided. So here are some results. Like the first thing we found for like multi-query, multi-token associative recall, which is like associative recall task, is that, of course, with softmax plus rope, which is like most models use, as we go to auto distribution, the model just fails. If you use NAPE instead, no, even with softmax, we start to get some really good generalization. And among all methods, like use Ascent-max, which is the one that we proposed, we get the best overall generalization, up to like 1,000 times generalization. So this is huge. For max retrieval, we also get similar findings. In here, we also compare like with top K, adaptive temperature, which is from the paper from Google, and other tests we have in the paper like copy, reverse, sort, etc. We basically see the same pattern. Right? First is that like NAPE helps a lot, and second, like the Ascent-max usually is the one that leads to best generalization. But what about language modeling? Right? So it trained some small models, some small transformer plus models on billions of tokens from this LLM. And what we found is that like for metrics that are based on perplexity, like lambda, you usually get like much better scores with sparse attention. Whereas for other tasks like LSWAG, PQA, ArcC, etc., like the scores are more like all more more on par with softmax. And we also like train the 1B models, and the trend is basically the same, like Ascent-max and Int-max. They outperform on Lambda in terms of perplexity, but in other data sets they are basically on par. We also tested on like archive data and PubMed, and the findings show that like Ascent-max is the one that leads to better perplexity among all data sets, basically. And the difference is quite big sometimes. We also look into ruler, so this kind of needle in the haystack evaluation, and Ascent-max performs really well. If you compare, like for instance, a recent paper from Mamba 3, which is on archive, and we can see like it for 4K here. So these models were all trained on 2K, so 4K is already out of distribution. If you look here, for instance, something like Mamba 3 or Gated.net, 4K, they get something like 99, 88, or cases we had like 100%. For the single 2 task here, for then like 4K, they get like something like 50. In our case, we get like 83. So in this, like it has much smaller model in less tokens used for training. So this is very promising. So yeah, as I said before, like if you look at this plot, we can see like the context length of current LLMs, or like they are skyrocketing. They are increasing exponentially. And another problem that this creates is the problem of scalability, right? So you don't need to look at all numbers in this table, but let me just highlight a few of them. So you can see like these models are getting bigger and bigger in terms of parameters. So this means that like more days to train, the price to train these models is like astronomically. So this is a big problem. But also like in terms of CO2 emissions, like this is, at least me, this concerns me a lot. And this is just for a single training run. So it's really important that we try to, scale these models in the best way we can. So there is like since like 2020, maybe even before that, like there were many papers proposing like efficient tension for transformers. And in particular, like I like this spot right here in this figure, which is something like, okay, we have some patterns that are not fixed, they are kind of learnable, they are adaptive, and they are also flexible. This would be like the dream spot, right? But turns out like all these approaches, they are not really used in practice because they always trade off some accuracy for efficiency. So yeah, I get some efficiency, but no, they are trade-offing some accuracy. So this is not desirable. Um, so let me talk a little bit about the types of sparse attention they usually have in the literature. One of these kind of attention is fixed patterns, something like local context, like just sliding window, or maybe like just global tokens. I always focus on like on the first columns of my attention matrix, or maybe some random patterns like Big Bird. So yeah, this is cool. This is like fast, of course, but it's like there is not a lot of adaptivity. Like it doesn't depend on input, so it's always this pattern, and like maybe for some tasks that pattern is not optimal. We can do some kind of dynamic selection to circumvent that. Something like doing top K, like using in NSA, or maybe like LSH, some kind of clustering. And yeah, I get more adaptivity with this, but it's not very flexible. Like for instance, k is always going to be like equal to 2. This is very arbitrary. But again, I lose differentiability, so that's really not good. Gains in terms of time cost and memory cost. And with Alpha-entmax, we get this sparse distribution view of sparse attention. So yeah, this is naturally sparse. It's adaptive, it's flexible because I can control this alpha parameter to induce more sparsity. It's fully differentiable. But the problem is that as recently, like the cost for computing this was like more than quadratic in time and quadratic in memory. So this was pretty bad. And this is because like for computing Alpha-entmax, we need to find this constant tau. For some specific values of alpha, we had like very efficient algorithms that require sorting. So that's why you get this log n term. But they are only available for like 1.5 in alpha is equal to 2. So only the 2 cases. And they require sorting, which means that they are not GPU friendly. So yeah, the idea is that, okay, maybe you can do something better by looking at what was actually like made a really good success in the literature, which was FlashAttention. So now I'll give like the word to Nuno, who is like one of the authors of Others Flash, and he can talk more about this.
Hey everyone. Yeah, I mean, many of you know FlashAttention. I mean, back in 2018, when the first Transformers models came out, they're usually around 1 to 2K tokens, which corresponds to your average Wikipedia page. And I mean, as soon as FlashAttention came out, models were started to scale. And while many things contribute to the scaling, FlashAttention was definitely one of the key enablers. I'm not going to talk too much about FlashAttention. I think many of you know, but there's these three main ideas, which is tiling. Your input matrices are usually too big to fit into shared memory, so you tile them and you compute attention with respect to each tile. There's also online softmax in the case of Softmax, which allows, for example, FlashAttention to compute in just a single pass over the queries, the keys, and the values. Yeah, FlashAttention was able to compute the exact attention output without having ever to materialize the matrix, the score matrices or the probability matrix, which were quadratic. So essentially, they solved the quadratic memory complexity. Of course, in the backward pass, you don't have these matrices S or P, so they just recompute. And what's funny is that these extra flops of having to recompute these matrices basically more than compensated for the fact that you don't have the overhead to need to store these big matrices in memory. So what we tried to do with Splash was do the same thing, but instead of having softmax, you'd have Alpha-entmax and gains those elegant properties of the function. Um, However, Alpha-entmax has a few caveats. So softmax has a closed form solution. Alpha-entmax, we have to find this tau, and this essentially is the concept that guarantees that our vector probability sums to 1. So this can correspond essentially to root finding problem. So all we need to do is to find the tau that finds the root of our function f here. And this is quite troublesome. Up until at a splash, what was usually done was something like this. So you'd have your input, you'd load it, you compute the maximum to initialize your tau, and then you would essentially load your input and refine the tau each time. What was used is essentially the bisection update, and which is very simple. You pick 2 points that guarantee that your root is inside those points, and you keep evaluating at the midpoint and update the bounds, and eventually you will converge to the solution. The problem is that it requires a lot of iterations. So in our experiments, it requires more than 20 iterations, which means that, for example, for attention, you'd have to compute the q times k 20 times, which is extremely expensive. But okay, once you have tau, you can simply compute the formula, and it's all nice. So our main objective here was, okay, this is inevitable. We need to refine our tau and compute tau, but let's try to minimize the number of iterations that it requires for us to get a good approximation of tau. So can we actually do better than bisection? What we looked at was looking at the derivative of Alpha-entmax. It's relatively easy, so it's a constant times the original function, so a shifted power of the original function. So if we could somehow use this derivative information to get a better estimation at each iteration, we could converge faster and reduce the number of iterations. And there's actually a family of methods that does that, the Householder family of methods. But one particular case is the Halley method, which obtains a cubic convergence rate, which is a lot better than the linear that we had from bisection. And all we need to do is to compute the two first derivatives, which are easy to accumulate in fast memory on the GPU. However, these methods are not guaranteed to converge. So in some cases, and theoretically it can happen, if you start too far from the original root, you can end up diverging, which is something that we don't want. So what we proposed was essentially to combine these two methods. So combine the cubic convergence of Halley's with the guarantee of convergence with bisection. So as in bisection, we keep our two bounds. They guarantee that we never leave those bounds. So the goal here is essentially to always compute the Halley method if we stay inside the bounds. Otherwise, we take the bisection update. So even in the worst case scenario, we end up converging. Empirically, that almost never happens, but it's good to have that guarantee. In terms of results, you can see here the plot. The mean absolute error compared with bisection alone is a lot better. We achieved essentially a 7-fold reduction on the number of iterations. So instead of having to do sort of like 20 iterations, we can do 2 to 3. So that is a big improvement. So one way you'd essentially compute a naive Alpha-entmax FlashAttention would be to use the same tools that FlashAttention did. So you use tiling and you load your input and you compute whatever you need. Of course, this is going to be strictly slower than FlashAttention because we need to compute this tau, we need to refine the tau, and that requires loading k at least 2 times and computing q times k at least 2 times. So can we actually do better? Can we, for example, use the sparsity that the Alpha-entmax function gives us to maybe gain some efficiency back? And that's what we try to do. So essentially, we still load k a few times to refine our tau, but once we have a good enough tau, we essentially keep track of which blocks, which tiles leads to non-zero entries. And when we're actually calculating the output, we can skip the loading of QV pairs, and skip is also its computation, so we gain some efficiency back. And we use this sort of a dynamic block mask, if you must. The good thing is that the entmax function also has a good property, which is the backward pass is also sparse. So the block mask that we use and calculate on the forward pass, we can also use to calculate the backward. What we did, we decided to separate the calculation of the gradients of Q and the gradients of K and V. So we can use the block mask and its transpose to essentially skip some computation. And if it is sparse, we can actually have a sort of almost like a subquadratic backward pass, which is something that Softmax cannot have. Yeah. So these were the initial results that we reported on the paper. So, I mean, usually in most cases we are slower than FlashAttention. We are only able to surpass it around 90% sparsity. Since then, we did a lot of improvements, and this is still work in progress, but it seems promising. And with some a few algorithm tweaks, we can actually get a lot better speed ups, and we can beat FlashAttention starting from around 50% block sparsity. In terms of performance of models trained with Alpha-entmax, we mainly saw some small experiments, but for example, in retrieval tasks, Alpha-entmax attention was able to surpass the Softmax attention by quite a large margin. For example, for the alpha equals 1.5 and alpha equals 2.0, we beat Softmax attention. And for language modeling, we trained the GPT-2 model, and it demonstrated a lower validation loss across all steps and better L-squared accuracy. And basically matches the runtime and memory requirements of the model trained with the FlashAttention, which is quite nice. So one thing that we looked at was the attention patterns of models trained with Alpha-entmax attention, and we saw something here. So here we can see basically the attention patterns of a single query. So this is entry-wise sparsity across all layers and across all heads. Other than the first layer, the model is extremely sparse, as low as 1% of non-zeros, which is very, very sparse. And the first layer seems to be more dense. This goes on par with what other works have reported in the past. But it is interesting to show that softmax attention does do a lot of redundant computation because these models were able to outperform softmax attention, and they only look at very few entries on the context. But you may ask, what about block sparsity? Do you actually see in models trained with max attention any block sparsity? And this is some recent experiments with a smaller llama 3 model, and we can see that, for example, in the first 12 layers, the layers like to be very dense. This goes on par with the last slide that I showed. But as we go, and the last 12 layers, for example, like to be very sparse. And they're usually at the regime where we read FlashAttention, which is pretty nice. And there's many layers that are over 60% of block sparsity. So while end-to-end, if we use always Alpha-entmax attention, we might not read FlashAttention because many of the heads like to be very dense. We're actively looking to other options, such as sort of hybrid models where in the initial layers we use softmax attention with FlashAttention, and then we switch to Alpha-entmax for the later ads. Yeah, I mean, maybe Rex can.
So yeah, so to finalize, like we see like, okay, Alpha-entmax is really cool. It's a mathematical principle. It also leads like to strong generalization. Like in Ruler, we saw that like it was even outperforming Mamba 3, which is a really recent work. In general, it's like on par. Like it's not going to like, oh, it's much better than Softmax, but it's usually like on par. But when we go to extremely long context, it has these very nice benefits of not suffering from dispersion, oversplashing, etc. At the splash, like you take a look, like we developed this in Triton, so this is not good. So we're comparing something like which was FlashAttention 2 at the time, which is like is the most more fair is the most fair comparison we can make in our version that is in Triton, and we were still able to to beat FlashAttention. Of course, we're in an academic budget, and this is like just the first version of the Splash, so we are actively pushing towards more efficient versions. So like there are many future directions from this. Like one thing is that we noticed that like some works are pointing that like maybe some sparse attention with sparse focusing can learn faster, like this work with Top K. So this can be pretty huge for data efficiency. There is like, as Nuno said, this mix of things in sparse attention layers. We're also looking into like decoding strategies with sparsity, like proper prefilling and generation. And yeah, stay tuned because we are going to launch more. We're going to launch more of the Splash versions that are more optimized in the future. Yeah, that's it. Thanks for your attention. I think you're muted.
Yeah, please feel to ask questions that in the chat. You can also mute your. Yeah.
Hi, I had a question in the chat about the sparsity rate. Thanks for the talk. It was really great. I guess my question was, since they're during generation instead of prefill or training, do you see an even better rate of speed? Because it seems to me like due to there only being a single query at a time, you might have less chance of like lots of blocks having something in them.
Yeah, I see.
Yeah, I mean,
Maybe you can answer.
Yes, we haven't looked too much into the inference. We're trying to look that. Yes, given that, for example, in the single query case where using multi-ad attention and not something like grouped query attention, we can use sparsity a lot better because we're not constrained to use tensor cores, and we can instead of having this restriction of everything in the block being 0, we can use more of an entry-wise, which sort of gives us some advantage because we have seen that this is extremely sparse when we're talking about entry-wise. So yeah, we're actively looking into maybe bringing some inference kernels and see whether we can, for example, beat flash decoding or something like that.
Yeah, exactly. So one thing that like just to complement that we are looking at is how to reduce the number of passes the maximum as possible, right? Because to compute, it's FlashAttention here, or like flash decoding here. Flash decoding only takes like one pass over Q and K and V, right? This is very hard to beat with sparse attention, but we can do it. We have some ongoing work, and yeah, it's possible.
Cool. Yeah, it sounds like very fertile ground, actually. So you guys have not had a chance to really experiment with inference and how sparse the memory access pattern would be?
At Inference-time, not yet. We have some ongoing work that shows that very promising results, but like nothing published, nothing. I need to take a closer look.
Cool. I'm excited to see it. I think it'll work really great.
Thank you.
Thank you.
Hello.
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 I've got a question. Thank you for your talk, and I just want to ask, is it possible to adapt a model trained with Softmax to Alpha-entmax with long context continuous pre-training? Because recently there are lots of papers working on this, and these papers are basically talking about that we don't really have to train a sparse attention from scratch, and we don't have to put the sparse attention from, for example, like a 4K context lens or 8K context lens per training stage. Instead of this, we can, for example, we train the model in 8K context lens, and then we expand the context lens to, for example, like 32K or 64K with sparse attention. Is it possible to do this with the Alpha-entmax attention?
Yes, 100%. Yes. In fact, like these experiments with the modern bird, we did exactly that. We started with a model that was dense with softmax, and we did continuous pre-training with sparse attention. And there are like lots of interesting research questions here, in my opinion, which is like, first is like if you take a look at Alpha-entmax, like if you go back like to the initial plots of Alpha-entmax, if you have like alpha close to 1, right, we recover softmax, right? So something that we did is like we initialize alpha to as 1. In that training progressed, we slowly increased alpha towards the value that we want, right? So this allows us to like just do a small continuous pre-training and make the model sparse using that strategy. But we are also investigating like other strategies, like for instance, maybe we can, instead of just like increasing alpha linearly, we could like have a bigger gaps, like alpha equals to 1.25 and then 1.5 and then 2, like, and with a higher learning rate, and this would allow us to like make the model sparse with even like fewer iterations, fewer data points.
I think with this kind of technique, probably you can maybe like try to adapt larger models, for example, like 3B or 8B models, because from my perspective, the long context continuous pre-training doesn't really need lots of tokens. For example, like 5B tokens or 10B tokens is not enough.
Yeah, that's true, exactly. So we are actually working on lots of things. One of the things is exactly that. I know that Nuno did some preliminary experiments on that, and yeah, like one of the things is like we can adjust the learning rate to make the model be sparse faster, and it seems to work. And yeah, that's definitely possible.
Yeah, thank you.
Thank you.
Thank you.
Yeah, I'm an author of a paper called Rad Lads that does this kind of training, distillation basically for regular transformers to linear type of attentions. And in that, you might find one technique we use interesting, which is that we can either lower the learning rate on the MLPs or even freeze them, and then raise the learning rate on the attention portion separately. And that seemed to allow us to very quickly get that kind of adaptation. So that might work well for you guys too, if you're not doing it already.
Yeah,
Okay.
that's very
That's
interesting.
interesting, yeah.
Let's take a look at that.
Yeah, we haven't looked at too many different ways of adapting.
Yeah.
I mean, most of the time the model does learn fine, but it'd be nice to have a way to get it to adapt quicker.
Yeah,
so
we're able to get stuff done in like 700 million tokens instead of like, you know,
Oh,
20 billion or
that
whatever.
is-
So it's very convenient. And we're doing a
Yeah,
bunch
that's
of other
very awesome.
stuff
Yeah.
using, sounds like we have a new version of it that's using some stuff like combinations with NAPE, like you guys are. And so it does seem to work really well. So I think you can get that to happen really quickly.
And how big was the model?
We've done it up to 70B.
Oh,
And it, you know, we've done that in like a day basically on on a node. Or maybe that one was 2 days. I forgot. Yeah, I think that one's 2 days.
Okay, that's very impressive.
Yeah, that is extremely, yeah.
Let's definitely take a look at that.
Yeah, that's really exciting to me also, to the ability to potentially take pre-trained models and convert to some version of this. Actually, that gave me another question, which is, did you guys ever experiment with alpha being trainable?
Oh, yeah. That's a really good question.
Yeah.
So like, yeah, we can turn alpha into a learnable parameter. And Nuno did some experiments also with that. And it's quite interesting because like in terms of the kernel, like when we have something that is like alpha equals 2, alpha is equal to 1.5, the expressions are all really neat. Like we don't have exponentials, like it's all quadratic in the like it's or linear, so we can get like maximum efficiency. So we were kind of, oh, maybe if we have like alpha that is learnable, like different values alpha, this is going to be slower. But in practice, it's not, right? We can just like use log and exponential tricks, and it works well. And in terms of like downstream test results, the experiments that Nuno did in language modeling, I think it was with GPT-2, right? It was outperforming like all these different variants that we had, like by a large margin actually. So that's also very promising.
Cool. What values of alpha did it seem to end up on? Did you go and inspect what the heads looked like?
Yeah, we did actually 2 experiments. One was so the alpha was for each ad, so each ad would learn its own alpha, which worked fine, but it seemed that the models were mostly around 1.5, the value, which we trained a lot of models around 1.5, so the difference was not too big. We also did another experiment which was to learn per position for each ad for each position. And that seemed to be the work the most well.
Sorry, could you explain what you mean by position in this context? Do you mean in the sequence?
Yeah, like each query is going to have like its own alpha.
Yeah.
So like in a fixed positional encoding sense, you gave each one.
No, like let's say in transformer like this KQ matrix, right?
Yeah.
So we map to like distribution row wise, right? So each row is going to have a different alpha.
So but that's matched to the absolute position of the query,
right? Yes.
Oh, okay. Interesting.
Yeah. But it would learn.
Did that end up working better?
Yeah.
Huh. That's so interesting, because then you come up with this problem of like, how do you extrapolate that, right?
Yeah, that is true. That is true. Yeah, that it doesn't have that. It has some disadvantages for sure.
Maybe I also have one question regarding the implementation side. I was wondering which size kernel size tail size you use for the query and the key value in your implementation.
I mean, usually we auto tune it with Triton for each context length and head dimension. We usually fix once we have the block mask, we usually fix it. But it can also be learned, like it can also be auto tuned. So maybe here, yeah, usually use 64 by 64 once we have the block mask, which work best for Ampere architectures. But we're now restrained to use 64 by 64. Of course, if you increase the block size, you'll get less sparsity. And if you decrease it, you'll get higher block sparsity. So it's always a trade-off, and the trade-off is not very like easy to predict, because it will depend on the inputs, right? But we are not restrained to use 64 by 64. Once we have the block mask, we can use, for example, 32 and 30 by 32, and then reuse the block mask. So 2 tiles will correspond to the same bit on the block mask.
I see. Yeah, because I think 16 times 16 is already large. Yeah, I think that it is maybe sufficient for the recent new hardware. Yeah. But it seems that in this case that we need maybe a very high sparsity ratio to ensure that there exist many blocks that they are purely 0. Yeah.
Indeed.
Yeah.
Like with the newer versions, like Like even like at 50%, which is like really, it's usually like very sparse. Like if you go 16 by 16, things are really, really, really sparse.
I think I agree. Yeah, I think that maybe something need to be done related to encourage maybe the block level sparsity. Yeah,
Indeed.
this makes sense. Yeah.
Yeah. You could think about like doing permutations or maybe learning permutations such that we lead to more block sparsity, right? But of course, like since we are dealing with positional encodings, we would need to make sure like the things like let's say if you use alibi, we need to make sure that after permuting we add the right bias, right?
Yeah.
So things get a little bit more complicated, but it's definitely possible.
I see. Yeah. And what's your idea on the reason, maybe the Flash mobile and the DeepSeek sparse attention? I think they are on another maybe different way. There's something like they are trying to maybe optimize some system kernel implementation so that they just means that they want to accommodate to more and more random sparsity, just not continuous one. Yeah, the more fine-grained ones. What's your idea maybe on these directions? Yeah. It seems that from their experience, they want to make it more fine grained, just then give the sparsity. Yeah.
Indeed.
Yeah, I mean, it'd be nice to because the sparsity entry wise is so big. Thing is, the tensor cores are getting so fast that if you're not using tensor cores, you're pretty much losing a lot of efficiency. But for example, I mean, again, the spot here, like as little as 1% of non-zeros is extremely sparse. But there's no way of doing this entry wise because not using tensor cores is very costly.
Yeah, I wonder though if you can, going back to my original question about the generation versus prefill, I wonder if even during training you could use fewer queries in a block than keys, because I think that might lead you to having more sparsity, and because it's so sparse, you can like kind of essentially end up having less memory access. I'm not sure.
Yeah,
Hard to
I
tell.
mean, NSA kind of did that, right, with group query attention, where they they force some sparsity on the queries. But yes, we actually haven't looked in group query attention, and the kernels do not yet support an efficient group query attention implementation. But for sure, that would be actually nice because that way you can use perhaps maybe more sparsity and still use the tensor cores.
Yeah, for sure. I'm just not sure if what he asked was about like if you use like a block size for queries that is smaller but then larger at the block end. Let's say I get some. So I would definitely get something that is more sparse.
Okay, I thought
because like I guarantee you get sparsity on the row level, but not column line.
I misunderstood.
Yeah, exactly.
That's a really nice insight indeed.
Yeah.
So maybe if you try tweaking like smaller blocks of queries, you might end up with just magically more efficient kernel.
Okay.
That's true. We didn't try that, and
we didn't try it.
Cool. Let me know. Curious to hear how it works out.
Yeah.
Thank you.
Let's try that. Thanks. That's a very nice insight.
Yeah, I've been doing a bunch of work on sort of more closer to top K type of things. And so I've been thinking a lot about like how the memory access patterns work for this stuff.
Cool.
Yeah, I think there's one more question in the channel that Nicola asked, can sparsity in the attention coefficients be achieved using sampling or something like straight through estimate or at least to non-smooth?
There's another question.
I think it's in the show.
Where is the shot? Can sparse attention coefficients be achieved using sampling?
Maybe Nicola can also unmute, to explain the question. Yeah, I think.
Yeah.
Yeah, sorry.
Yeah, you can ask Nicola.
Basically, like rather than taking the multiplying the attention coefficients by the value, could you sample, and then basically literally just selecting the top.
So you sample what exactly? You sample
because the attention weights parameterize like a categorical distribution, so you can sample that.
I see. Um, definitely yes, it's possible. The thing is, how you do that sampling, I think is not, if you want something that you sample when it is sparse, I'm not sure if that's easy to do. And you'll definitely need some kind of, surrogate gradients or maybe like some reparameterization trick to make it work in the backward pass. I know that, Andre Martins has a very nice paper where he explores this idea of having something that he calls mixed distributions. So that's something that you can sample and is guaranteed to be sparse. It's like the concrete, the concrete distribution. It's like the concrete distribution for is n-dimensional.
Which distribution?
The concrete.
Okay, I have not heard of it. Thanks.
Yeah.
I had one other question. I haven't gotten a chance to read through the paper and look at the math yet, so I don't know if this makes sense. But in the calculation of tau, how sensitive is this to tau being wrong?
Yeah, that's a nice question.
Yeah.
Well, from our experiments, not that much. For example, we tried using just one single iteration, which the estimation of tau is, well, clearly wrong, right? And it'll get you the wrong output. So the sum will likely be maybe a little bit bigger than 1 or a little bit smaller than 1. But the end performance of the model didn't deteriorate. Maybe a little bit, but not significantly. So
right, and you still have no negative values, so it all works out, right?
Yeah.
Okay. Okay, that's interesting. And so does that essentially just changing tau to be incorrect, that essentially changes kind of how sparse it ended up being?
Yes.
Okay.
If
So
you
it doesn't actually like make the other values like relatively incorrect or anything. It just adds more or takes fewer, essentially. It changes kind of the equivalent of top K to change K.
Exactly. But
Gotcha.
yeah, they did, like, if you're approaching tau from the left, right? So it's smaller than the goal tau. You're going to get something that is more dense, right? And if you approach from the right, it's going to get something that is more sparse than the optimal distribution.
Yeah, so I guess this leads me to the question I really had, which is, can we just get tau in some kind of fake way that doesn't actually calculate it at all? And can you essentially learn tau based on either as a function of Q, like as a function of X, or
Indeed.
in
So
some
this is
other
a good
capacity,
question.
including maybe the length of the context window? So like tau might relate both in a learned way to both the length of context plus also something about the input.
I see. That's very interesting. Like something
Because
that
then you would get rid of your entire problem with the speed, right?
indeed.
No
I
multiple
see where
K
you're going,
access
and
or anything.
we've been thinking
Yeah.
about this a lot as well.
Cool.
And the thing is that, like, if you have something that, like, let's say a small MLP on the side or linear layer that tries to predict tau, giving like maybe the context length and Q and K, etc. Yeah, you can get some estimate for tau, but like there are no guarantees at all that it's going to be a good tau. So maybe some case you're going to get something like one hot distribution, and their case is going to be fully dense. So it's really hard to control for having a good tau in this case, and even if you're learning, so it's not easy. But there are there are ways in where we are actively looking to ways that we can extract the maximum information as possible from our queries and our keys that allow us to do maybe like just one pass and maybe not even one pass, just get the initial tau that we got from the first pass, and that's reasonably quite good, and we can move on.
Cool. Yeah, that'd be great.
Yeah.
Yeah, also can imagine some other methods where maybe this doesn't work for training. I didn't really think it through, but where you estimate tau, and then if essentially you end up with too small a top k, you just do it over and either, change. Essentially, that's like your, incremental calculation of tau is like, well, we got a bad result, so let's just, try a bigger tau or whatever, or smaller tau or whatever.
Indeed. Yeah, though that I think that implementing that, at least in Triton, that might be a little bit complicated, like because you need to load all keys once and again to know that okay, that's good or not. And
Yeah, I can imagine how it would be easy during inference, but maybe really, really hard during training, just because you're trying to do, or pre-filled, because you're just trying to do everything in parallel. So
Indeed.
you would have to, a whole block of queries could get messed up if it's wrong, I guess. And I guess another thing that'd be interesting to investigate if you haven't is how much tau changes from query to query within a small group of them. Because like co-located queries might have similar tau values.
I see. I mean, yeah, that's a good question.
I actually
Yeah,
doubt that from
we
my
haven't looked
experience, I
at-
doubt that it does have similar values because essentially some queries are looking for like a very specific thing in the past and some are very non-specific. And
Indeed.
so I think tau may actually vary quite widely there, but
Yeah,
I mean,
it really
might be
depends
worth
on
checking.
it really depends on the head. Like maybe some heads they have like a pattern that is like highly predictable and highly local, so that would be the case. But some heads definitely not.
Yeah, actually, that's another interesting point of view on that is that you may be able to get sort of sparsity in terms of the model. This is something I have experienced is that different usually something like half the heads aren't that sensitive to a lot of stuff. And so if it may be that some heads, yeah, you can have just a learned tau and some heads you need to have like a calculated tau. That might, dramatically speed up the model if tau calculation ends up being like a significant cost. I guess it can be a little hard to balance the compute that way because you're going to have, you might have like a random number of heads within a given layer that need tau versus need a compute tau. So
Indeed. Yeah.
No, but it would be interesting to look into those statistics. We actually haven't had the
Yeah.
chance to, but yeah.
cool. This
Yeah,
seems like
sure.
such fertile ground for so many interesting things. I'm really excited to see where you guys go with it.
Thanks.
Thank you
Thanks
so
a
much.
lot.
Oh, I've got a question based on the discussion of the last question. Is that in existing papers, there are lots of papers indicating that different heads are basically like playing different roles in the model. And in traditional transformer architecture, in the traditional attention mechanism, the different heads are like highly correlated. For example, like when there's one head playing a role as the attention sink, and there's another head also playing a role as an attention sink. So have you ever observed this kind of phenomenon in the Alpha and Softmax mechanism?
Well, I'm not sure if you try to see some kind of like exactly patterns for the heads, but I would assume that it would happen as well. For instance, attention sinks would happen as well for Alpha-entmax. At least the way I see attention sinks is that like they are manifested at Softmax, Alpha-entmax, that's the attention part, but the root cause is somewhere else, is something else. So they are manifested like they are going to be manifested as well in Alpha-entmax. At
Yeah,
least attention
exactly.
sinks. Yeah.
I think lots of people are not people think that the attention sink are not a good thing. People are trying to eliminate the attention sink right now.
Indeed.
Yeah, I'm surprised to hear you guys say that you think attention sinks will still exist in this method. Did you observe that, or is that just based on your gut feeling?
This is based on my gut feeling. I don't know if
Yeah,
it's
we didn't check that.
Yeah, like this is on my gut feeling. Like my gut feeling tells me that this is a problem that comes from maybe the logit space. So the way I see it, like at least me personally, I see attention sync is like, okay, I have a head that wants to do a no op, right? So it puts all mess in a token that is like, okay, is the only token that is always in there, like maybe the beginning of sentence token or maybe punctuations or something. And he tries to like erase this information by putting all mess in this token. So my intuition says that, okay, even if you have entmax, is sparse, of course, but it's still a probability distribution. It still has to sum to one, so it's still going to attend over something. So my gut feeling tells me that the attention sinks will still exist with Alpha-entmax.
That's interesting. So maybe it would be sparse and only choose, say, like one thing, but that one thing would be the attention sink is kind of the idea.
Exactly. Mm-hmm.
Neat.
That's it. I think that if there's no more questions, that maybe we can end. Yeah. Thanks for the good talk and maybe the very long discussion. Yeah, it is very helpful. Yeah. Thank you very much. Yeah, for your time.
Thank you.
Thank you all.
Thank you, everyone. Thank you.